The objective of this webinar is to know the fundamentals of line differential protection. We will talk about current differential relays. We will also talk about line current differential relays, and then we will have some application issues addressed in this presentation. The agenda for this webinar is that first of all we will start with the introduction, and then some words about differential protection in general, and then we will be specifically talking about line current differential relay, and then application issues, and the important part of line differential protection is obviously the communication of that, so we will talk about that. And then at the end of the presentation, we will summarize the important points. So line differential protection, so this is the basic idea of line differential protection. You have station A and station B, and between that you have a transmission line, you have two breakers, one breaker on the substation A side, another breaker on the substation B side, two CTs connected on each side of it, and a differential, line differential protection box connected to this CT at station A, and then another box connected to this CT on the station B side, and then these two guys will talk through certain communication medium to exchange information about the analog and sometimes the digital data, the binary data for these two relays. So that's the basic idea of line differential protection. So what are the elements of line differential protection, multi-terminal line differential protection? So it is essentially a unit protection. So when we say about unit protection, so all the differential protections are normally unit protections, and they are inherently very selective, and the boundaries of the protections are defined by the location of the CTs. But still, in the let's say in the ideal world, that would be that there shouldn't be any problem of discrimination of the fault between within the protection zone and out of the protection zone. But that would be an ideal situation. But in practical terms, there are several scenarios in which to identify whether the fault is within the protection zone or out of the protection zone, it might be a little bit tricky. So to determine whether the fault is within the protection zone or out of the differential protection zone, that is a task, and then we will talk about it in detail, that what type of techniques we use in ABB protection relays to determine whether the protection is within the zone or out of the zone. In line differential protection, you can have obviously an element of an equipment transmission line which needs to be protected, but also in certain cases you have the power transformer within the protection zone as well. So having a power transformer within the protection zone of line differential protection imposes some more issues, and those issues need to be addressed, and we will talk about it. What it essentially does, it measures the currents at the terminals of the protected circuit, and then transmits the information about the currents to the remote ends. I mean, if it is two line ends, then we have one remote end. If it is more than two up till 5 line ends, our ABB line protection can handle. So we'll have 4 other remote ends. And also it compares the currents using the classical differential protection principle. And then, of course, we have to supplement that current differential principles by some additional criteria to cater the needs of specifics. And inherently, this differential protection, line differential protection, is highly dependable. And when we say dependability, it means that it will operate for all the intended faults for which this relay is intended. And it is also highly secure, which means that it will not operate for the faults which it's not intended to. So, so this is something which is, these are the 2 terminologies which are normally used in the protection world quite often. Also, this line differential protection is quite good for evolving faults as well as for cross-country faults. And unlike distance protection, line differential protection is immune to power swings, mutual coupling, and series impedances unbalances. Because of this numerical technology, now we can transmit the sample data, and therefore we can calculate the sequence components as well as the harmonic components of the measured analog values. So right now, as we talked about it, that this is the local station. We have to define in line differential protection scheme that what is the local station and what is the remote station. So this is the box which is measuring the local current, and it is getting the information from the remote and relay, and then it is processing the information in this box. So there are different topologies, and we will talk about it, different way of communication, that also we will talk about it. But the basic idea is that the box takes the information locally, and then it takes the information remotely from the remote end, and then processes the information and compares it with the threshold values to get into a decision of tripping or not. So as this line differential protection is basically a current-only scheme, so there is no dependency on the VTs. So it means that we do not have to worry about the fuse failure protection and CCVT issues or power swing issues. Yeah, VTs can be connected in line differential protection scheme, but just for the measurements purposes, or but the main line differential protection does not really take care of the voltage information. And it can be very, very sensitive in detecting the ground faults. And we will talk about it, that how we can really detect very sensitive ground faults as well by using this line differential protection scheme. As it calculates the values and the differential as well as the stabilization current values per phase, so that's why the information is phase segregated, and it is then ideal for the evolving faults as well as for the cross-country faults. And then as we have the measurements on phase segregated basis, so that's why we can have single pole tripping as well. And because it is not dependent upon the measuring of the impedances of the line, so that's why the series compensated lines will also have no impact on the line differential protection scheme. The only disadvantage of line differential protection scheme is the communication part of it, that if we lose for some reason communication, then we will lose the line differential protection, and then we'll have to fall back on some other types of protections like distance protection, or maybe in some cases just the overcurrent or feeder protection only. So, but with the advancement which we are making in the communication technology, this line differential protection is becoming more and more popular as compared to, for example, distance protection. But in high voltage or extra high voltage lines, of course, both of these protection schemes are used, with main as line differential protection and backup as distance protection. Types of current-only schemes, current differential can be analog or digital, and you can compare the phases as well, but that's something which is not really popular nowadays. So we will move on to the next slide. So here we have this current differential diagram. As you can see from here that IL is the local current, and if CT is connected with this dot notation, then if the current is flowing in this direction, the CT secondary current will be flowing in the other direction, and then IL is moving from here to here, and then IR is the remote current direction, and with this current notation, dot notation, then IR is moving in this direction, and the relay operating coil is in the differential path of these two circuits. And as you can see that IL plus IR will flow through the operating coil of this differential protection relay. And this is the protected object, and that protected object can be transmission line in case of line differential protection, or in case of other protected equipment like transformer or anything like that. So that would be the protected object. But basically the idea of differential protection is the same. So this would be the ideal situation, and when these CTs are actually have the ideal characteristics. So in this case, if the fault is external, then if the fault is somewhere here, external, then the direction of IL will remain the same, but the direction of IR will reverse, 180-degree opposite. So in that case, IL will be equal to minus IR. So therefore, if we add up these two currents, then the resultant would be 0, and therefore there will be no trip. This is the local current, and remote current is 180-degree opposite. So if we add it, these two diagrams, so then we will result into a 0 differential current. So there will be no trip. But in the other case, if the fault is internal, like the figure shown over here, if the fault is somewhere here between these two CTs, then in that case, the algebraic sum or vectorical sum of both these IL and IR will flow through the operating coil of the relay, and then relay will operate. So there will be a trip. So you can see the local end current oscillograph and the remote end oscillograph, they are both the same, so they will add up, and it will not be equal to 0. They will add up and to have a certain value, and therefore tripping will occur. So that was the ideal situation if the CTs are behaving ideally as per their characteristics. And that would be in the operating and restraining region, IL over IR, so that would be -1, and that would be in the restraining point. So in this case, we will have a very high security for the external faults, and at the same time, very high sensitivity for the internal faults. But because of the fact that we do not have the ideal situation, and there can be some errors, and we will talk about it in detail about these CTs. So therefore, we have to introduce the restraining winding also into the differential scheme, which will provide more stability to the differential protection scheme. So we will have to add these two restraining coils into the circuit. In that case, what will happen is that the same differential current will flow from the operating coil, but it will have an additional restraining currents which will improve the stabilization. So the tripping will occur only if the vectorical sum IL plus IR is greater than or equal to the absolute values of IL and IR together with the K factor. So K will determine the slope of the characteristic.